Welcome to today's webinar. The topic today is Introduction to Interface RFEM6, Tekla Structures. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal software company. For instance, the webinars, newsletters, website, and so on. I will be the moderator today and will answer your questions together with Lukas. Paul will do the presentation, but my two colleagues can introduce themselves.
Yes, hello also from my side. My name is Lukas. I work for Dlubal for 12 years now. I'm working here as a product engineer and customer support engineer, usually with the focus on the interfaces. And yeah, today I will try to answer your questions.
Also, hello from my side. My name is Paul Sibolgin. I support product development in the area of interfaces together with Lukas. And today I'm gonna give you the introduction to the interface between RFEM6 and Tekla Structures.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. Some words about how you can ask questions via the control panel on the right side of your screen. You can show that with that arrow, and then you can enter a question here. If you don't get an answer during the webinar, because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, then I hand over the screen to Paul. Just a moment. Paul, you can start now. Okay, thank you.
Thank you, Andreas. Hello, the following content for today. First, we start with some general information about the interface itself, about the installation, the functionality, and then we're gonna export a Tekla model to RFEM. We will look how we can get the analysis model in Tekla. And when we exported the model to RFEM, we're gonna adjust the model and add loads and design some members. And afterwards, we wanna pass these adjustments back to Tekla with an update function we implemented. So yeah, that's all for the content. So let's start with some general information about the interface. Our interface, where's my mouse? Okay, our interface supports the Tekla versions 2021 and 2024. It's a direct interface based on the web services. So we do not create a file of a certain type, but we transfer the model direct from one program to another. So to do this, you need to have Tekla and RFEM. To do this, Tekla and RFEM must be open on one PC. Yeah, to transfer the data from Tekla to RFEM or from RFEM to Tekla. The installation of the interface must be done manually. So after the RFEM installation, you find under this following path a setup file. You need to run this setup file, and a Dlubal tab will appear in your Tekla ribbon. And both import and also the export is started from Tekla, from the Tekla ribbon. And the last step is to check the necessary options for the interface. So you need to check your program options in RFEM6 and activate the web service option. And after that, that's all for the setup of the interface. And now it's ready to use. So next question is, what information can we transfer from Tekla to RFEM? These are the main objects. We can transfer members and surfaces, also the informations about the sections and the materials. And when we use the analysis model in Tekla, we can also already define supports, hinges, or rigid links in Tekla and export this information to RFEM. So let's look at the export options for the export from Tekla to RFEM. We have the following export options available. We have two types of model we can export. We have the physical model. It's like a CAD solid model which does not take into account the actual positions. So elements are not automatically connected to each other at their intersections, since we are only referring to the axis of the physical elements. And this is something I want maybe to show you. So if we have a model, a physical model, for example, like this, and the wall meets the ceiling. In this physical model, the wall meets the ceiling at the bottom edge of the wall meets the ceiling at the bottom edge of the ceiling, the black one here, and this is the physical model. And with a structural model, we require an intersection between these two axes of the models. So if we export only the physical model, we get some connection problems in these areas. And to solve this kind of connection problems, we have the option to generate an analytical model in Tekla and export this analytical model. So with this analytical model, you get, maybe I show this here. So here we can also export the analytical model, and with this analytical model, you get adjusted, call it line model with defined X positions. So every elements will be connected, and you can just export this model and keep on working on the structure. We can also transfer rigid links we generated in the Tekla model to RFEM. So when analytical model elements are not aligned or a rigid connection is created in Tekla, we can just transfer it to RFEM. And some cross sections are the same cross sections in RFEM summarized in one cross section number in RFEM. So with this option, you can separate it and get a individual cross section number for each member from Tekla. The Z-axis in Tekla is aligned upwards. So with this, we are just aligned the global Z-axis in RFEM also upwards. And when we export the Tekla model, we can create a new model in RFEM, or we can, if we have a model opened, we can override an existing model. So that's all for the export options. If we import a model from RFEM to Tekla, we have the following options available for now. We have three options for the import type. We can override a model, we can extend a model, or we can update changes we made in the model. The update have some separate settings we can adjust. So we can update the coordinates, we can also update the materials and cross section, and also new added objects in RFEM are added, or if we delete objects in RFEM, they can be removed also in Tekla. What I'm showing here is for now an intern version of the interface. So the update function will be available next week in the customer version. So for now, maybe it's for you still grayed out in the actual version. And we have also the option to generate an analysis model from the RFEM model if we import it to Tekla. So, and if we extending a model or overwriting existing model, we can also mirror the elements if we want it in X, Y, or Z direction. Yeah, that's for the import options. Now we go on with the conversion tables. RFEM and Tekla use different names for the same materials and sections. So if we want to convert one material or section from one software to another, we need to define the conversions we like to use. So here you can see a left column and a right column. The left column, it controls the conversion from the export from Tekla to RFEM, and the right column controls the conversion for the import from RFEM to Tekla. We have also subdivision from material and sections. And for example, here you see a Tekla name, a name profile for Tekla profile, and here's the same profile with a RFEM name. So it's sometimes different, and so that's why we need a conversion, but it would be a lot of work to define a conversion for every section we use in Tekla. So therefore we have regular expressions we can use that allow us to convert multiple objects with one entry in this table. And for this, we also have a documentation on our website. I will show you. Here you can see the regular expression we use. So for example, if we use the IPE 120 in Tekla and want an IPE 120 in RFEM, we can define this as a conversion, like here in the table. But if we want to create a conversion for the entire cross-section series, we can use one expression to cover every IPE profile. So it's very simple. We have just this regular expression. We use this kind of expression. And for this, we can entry any number we want, the 200, 300. And for the RFEM name, we express with this expression, we refer to the number we entered inside Tekla. So, and here you can see it in the conversion table defined. And only with this small entry, you have every profile defined for your conversion. And yeah, the most common materials, like you see here, are already defined with the installation of your add-on. So you don't have to define it yourself. But if you use different cross-sections or materials, you can always define your own conversions, and you only need to define them once and use them in all your future projects. So that's all for the functionality of the interface. Now we want to look very quick at the overview how we can apply this in a workflow. So a possible workflow may be that we generate an analytical model in Tekla. We define information about the cross sections, about the materials, about the supports, hinges, member types, and all rigid links. Then we can export this rule model to this complete model to RFEM. We can modify this model. We can add members or define loads and design the structure and optimize it. And every change we made, we can transfer back to Tekla with the update function. So every change to sections, material, or new added objects can be updated in this Tekla model. So if we want to look only, for example, at the steel model in Tekla, we can also generate different analytical models independent from each other. So we can only export one part of the model to RFEM and only look at this one part in RFEM and apply modifications and additions, and also update only this part of the Tekla model. Last maybe possible workflow would be if we define a structure in RFEM and want to export it to Tekla. We can also export the whole model or a part of the model to Tekla, and if there are any changes made afterwards, you can also export them to Tekla with this update function. And yeah, that's all for the presentation in this PowerPoint. We switch over to Tekla. So here we have a model. So if you installed the interface with the setup files showed in the presentation, you find this Dlubal tab on your Tekla ribbon. And here you see the things we talked about, the import from import options, the export options I showed you, and also the conversion tables. So first thing I want you to show what happens if we export this physical model without generating any analysis model. So I have an RFEM file opened, so I can export just this physical model and overwrite the RFEM file. If we start the export, we will see that RFEM gets logged down here. Gonna start now, I guess. Yeah, it gets logged, so the data is transferred to RFEM. And if you look maybe at this beam and this column, we see that the beam is connected to the flange of the column. So when we transfer it like this to RFEM, we also see that this beam is connected to the flange of these columns. But if we look at the line model in RFEM, we see that we are missing this connection from the analysis model here. So therefore, it's a better way to use this analytical model in Tekla. And that's the first thing we want to do. You want to generate this analytical model in Tekla and look how we can work with it. So if we want this model, we go to Analysis and Design. Here you see this analysis model and design models. And here you can define some basic properties. First, we can create a new model. Very simple. And here we can define some basic properties. Here you don't need to choose something. That's some old presets from RFEM 5. So this preset is completely fine. Only thing we can maybe do is to define the name for our model. I will name it steel because we only look at the steel construction today. Then you can press OK, and this analysis model is generated inside here. So it had still 0 parts because we need to select objects and add them to this model. So we now just could select our steel model and add it to this analysis model, but some tip if you generate this analytical model, because some note from my side is if you already defined some components in your model, like here, there may be a problem if you just mark your whole model and define and generate this analysis model, because sometimes, like in this component, this plate is defined as a profile, and here you see this plate is only defined as normal profile. And when we generate this analytical model, we also generate analytical elements for these profiles, and we want to avoid this because we want only this analysis model for the general steel structure. That's why you can deactivate the selection of the components. So if you select your model, the component is not selected and not and no model is generated for this component. That's what we don't want. So if we deselect these components, we can now stop this and say, okay, we want to select all these objects, this deconstruction, and say add selected objects. And now you see, make it smaller. Here we have these blue elements. So the analytical elements are generated in the axis of the beams and the columns. And now we can work with this. Now we will show you how we can work with this model. So at first we can double click on one of these elements and we go to the properties from the beams, or we move to the properties from the columns. And when we open these properties, we have some settings we can make. At first, we can define here in the analysis, the class, the member type for RFEM. We have the definition for a normal member type beam, or a truss, or a compression member, or a tension member. So for our structure, we want to define some truss members. For this, we gonna look at our model from the top, and all beams are orientated in this direction. We gonna select them, and now we can say, okay, we want these settings for our analysis beams, and we marked our beams and say, okay, we want to modify these beams and set the class to beam truss. So the member type is set to truss later in RFEM. We can modify this member, say apply, okay. And now you see they are green colored, so that's our truss members. What else can we define? We can define supports. The support for the columns here. The supports can be defined in the properties of the column or in the properties of the node. I can show you here. If you double click the node, you have the node properties, and here also can define the support. But the basic settings are that you define your supports in the properties of the column. So we have a start release and an end release. It's declared so that this yellow square shows you where the start release is, and this purple square shows you where the end release is, so you always know which node you're working on. So here we have some support condition. We can define a support, or we also can define a hinge if we want. So it's maybe some work to always define your hinge you want to use, or you often use in RFEM. That's why it's useful to get some presets like I did. So I define me the typical RFEM supports inside Tekla, so I can just load these properties into my model. So I want a hinge support. You can say, okay, I want to load these properties, and this will load inside here. That's the definition for the hinge support. And now I just can say, okay, I mark all my columns. Okay, I have every column, and say, okay, I want to modify these columns and add a hinge support at the start, at the yellow square. So modify and apply. Okay, now we have a support for all our columns. It's worked the same way for our beams. So it's the same principle. And here you have here the member type, and you also can, as said, define hinges. So for this, I also have presets for my hinges defined. So that's the typical presets, typical hinges from RFEM I use. So you don't have always start and to define it and lose some time. So for here, we also want some supports on this end of the beam. So I say I want a roller in X. I can load these properties in my beam properties, yeah, and mark these beams I want to adjust and say, okay, I want these properties modified onto selected beams. Now this is modified, say apply, okay. And that's all. That's the model is now kind of ready. And something we need to check is that we have generated this model automatically. So maybe we need to check if every connection is okay, if it looks like we want it to have. And to make it easier, you can again open this model settings. You see some display warnings down here. So if there are some errors in this model, you can just display them. And here you see, okay, there were warnings, errors in the model creation. Warning member is shorter than the minimum length. We can look at the details of this warning. And here, we make this smaller. Here you see the warning member is shorter than the minimum length. And now you can select which member is affected by this warning. Here it's a very simple model, so you always directly see which member is where the error comes from. If you select this part and can't see the mark in your model, you can also zoom to the analytical part, zoom in, and now you see it's this beam. And when we zoom in, we see there is an intersection and we have two nodes generated. So this node, maybe I change the view. Yeah, this node connects these 4 members, and this node connects these 3 members. So there's some error, and if we look at these members here from the other node, we see that the analytical element of this beam is not exactly in the axis of the element of the column. So if the axes don't meet at one point, Tekla generate a rigid link. So if the axis of these members, this member and this member, don't meet at one point, this rigid link, this red circle is generated. And sometimes it's useful, but in our example, it's just a mistake in the model. So we can move this analytical model into axis of the columns again. And how we do this, it's the better way to go back to a point where a lot of members are connected. So in this case, we want to move this connection to this node, and therefore we can just mark these 2 nodes and say we want to merge select nodes. We can pick the merge target node. We can pick this node, and afterwards, okay, we are not allowed to, by current settings, to move the axis. We say we will allow it for this case, and you see this axis moved. So if we look back at this side, there are no rigid link anymore, and so the axis of this member is in the same axis as the analytical part from the column. So that's some way to remove some of these intersections. And it's important to notice that only the analytical model is moved. The physical model we draw it here or we get from the constructor are not moved if we work on this analytical parts. So, and when we open our model again here, we see there are no warnings. And that means that's everything okay, and we can keep on working. And just other hand from my side, if you define this analytical columns, map beams, and so on, you have also the possibility to move them or change the location the axis is defined. It here is always the neutral axis of the physical member, so you can say I want it at the top center to be defined. You can say modify, and this will move to the top center for your beams, or you want to say I want it on the bottom center, you can move it there. The basic standard is always the neutral axis. And if you want to move it freely, you can also use the offset, so you can move it directly in the X, Y, or Z direction if you need it. But we want to keep it like it is here. So that's it for the analytical model. We can transfer it now to RFEM. And some last information, we use IPE profiles and a material. This is also already defined in our conversion tables. So these definitions are already inside if you install this interface. So there's nothing you have to do. And yeah, that's all for the analytical model. Now we can export it to RFEM. So we choose this analytical model, and we don't have any widget links, so it's not affect us. And now we all write our bad physical model, I would say, in RFEM. So the currently open model will be all written. You will see the RFEM is again locked, and the model is transferred directly from Tekla. And now we can look at this model in RFEM. So what we can see the supports are exported from here and from the columns and also from the beams. We see that our sections exported, the member type also exported, and also the material is also exported. So everything is ready. We can just go on working with this model. And what's the first thing you want to do? If I will display it like this. First thing we want to do is define a bracing for the structure. So for this, I define a new member. I'll define a tension member and define a new section for this member. We define a bar section. We choose this one in R20, and we can now use this section for bracing. And I want to define it here. Some bracing. Define here some bracing. And also this area. And finally, also at the back side, our structure. So now I would say the structure is completed. And what's the next step? If a structure is completed, now we can add some loads to the structure. For the loads, at first we want to go to the base data and activate the combination wizard. Okay, because we want to use combination wizards. And before we define the load, we need to find our load cases in our combinations. So let's start with this. First of all, I want to change it to Germany. And activate the combination wizard. Go on with the load cases and let me check. Okay, so the first load case would be the self-weight. It's already inside here, so we don't have to find any loads for this. I give it a name, self-weight. Then we want to create, okay, I forgot something. We need to define the static analysis settings at first. So that's just simple settings. We just confirm them and define two other load cases. Now we want the load case for the imposed load. This will be our imposed load. And as an example, we want some snow loads on our structure. So with this, we define the load cases. The action categories are assigned already. And we want to look at only the ULS design situation. So we just want to delete this one from our design situations and only look at this. And for combination, for our load combination, we can use this wizard. So we can define again the static analysis settings. I define some new and look at the second and define the analysis type as second order for our combinations. Okay. Now we have here our combinations. Let me check something. Okay. Yeah, we can say, okay, that's ready. So now we have here defined our self-weight load case, imposed load case, and our snow load case. So let's start with the imposed load. For the imposed load, I would like to use some load wizards. So we can generate member loads from an area load we define. So let's start with this. So we generate this into the load case number 2. It's already assigned. And we want a load magnitude of 5 kilonewton. And we need to define it negative in the Z direction because our Z direction is looking upwards, like in Tekla. So it's a negative value. And afterwards, we want to select our boundary lines for the plane. So we can select the corner nodes in the graphic. So I want my imposed load to be placed inside here. Okay, I will say okay. And now you see here our imposed load. You can make it a little bit smaller so it looks not so big. And if you want to look how it's separated on the member, you can display it separately. So you can make it again a little smaller. And here you see how the area load is working on the members. Okay, so this looks cleaner. After this, we want to define. So okay, we have our self-weight, we have our imposed load. We want now to define the snow load. For the snow load, you can also use a load wizard. Open the load wizard, we can define our roof type and our roof corners. and we have at first, let me check. Yeah, we have this roof at the top side of the building. I would call it, oops, roof run. And for the snow load, we can define the parameters. And wait a minute, I need to check something. I think I forgot to activate the load wizard combination. Now it's activated. So where does it take the parameter from? Ah, okay. I forgot to define the German settings, the German standard for the load wizards. So I could not do it like I wanted. Okay, my bad. Now we can look like this. Okay. Yeah, for the snow load, we can define a manual value if we have one, and if we don't know it, we can just use the snow load map from our GeoZone tool. So you can select your location. I select my location, and you get the zone data loaded inside RFEM, and now you will see that we get a value for our snow load from our location we selected. The load case is designed automatically as a snow load case, and here is the result. Here you can see the results for the snow load and the shape coefficient, and you can apply this. Now it's this value on our snow load. Now we want the snow load also on this part of the roof and also on this part of the roof. So we can just copy this in this list and say this is our roof number 2 and this is our roof number 3. And now we need to change the corner of the roof. So we select this part of the roof for roof number 2, and roof number 3 is this part of the structure. So I apply. Now we can check before we closing the settings. Is everything okay? We have now here the snow load here and here. It's fine. We can say okay. That's how we want it. And the next step, yeah, would be the design. So what we have done, we have a structure, added some material as the bracing. We have added the load combinations, the load case and the loads. And now we can begin to start with the design. It's just for first at all, we need to activate our steel design add-on. Okay, and now we only want to look at the cross section design. So for this, we go into the steel folder, to the ultimate configuration, and say we don't want to perform stability design. Say okay, and afterwards you can find in this table the steel design tab. You can open this and you can see every input data you need for the steel design. So we have our design situation, we have our objects we want to design. We want to design all objects. We have our used material, and we see also our sections. So I'm gonna start it now. So shows the results. First, it calculates the load cases. They are not calculated yet, and the load combinations. you will see here, it's our load combinations, and afterwards the steel designs also calculated. Yeah, that's all. So here you see the results. We see that the design check ratio is very high. So we need to change something of the profile sizes maybe. So we can maybe don't show the loads and look at the member where the ratio is higher than 1. These members only show selected objects. So now we see these members are the design check ratio of the member is too big. So we can adjust this cross section we use here until the design check ratio is smaller than 1. But we don't have to do this manually because we can adjust this process automatically. So if we go back to the input data from our steel design inside this table, we have our cross sections we use. So this one are the IPE 118, this one. And now we can say use another section for this design. And here we have the option to choose optimize. And when with this optimize setting, we say like find us the smallest possible cross section for the profile row, for the profile IPE series that fulfills this design checks. So we can just say optimize as this profile and start the calculation again. So here you will see that this optimization process will start. Optimization. And now we see it look even better. We have no red colors inside here, so it's always a good sign. And when we look back into this input data where we started the optimization for the IPE 118, we see with the IPE 240, this design situation will be okay. So we can say, okay, we want to assign this member or this section and say use all optimized section in this model. So the IPE 240 will be assigned to our model where it's needed. So it changed. Now we have to start the calculation again because we have also now a different self-weight, the model. It's gonna be ready in some seconds. Now you see everything is okay with this profile, so we can use it for our structure. And if you say, oh, this a very big ratio is way too big for me, you have the possibility to adjust it. So in this, if you're again at the input data where we choose this optimization, we have the global settings for the add-on, and here you can select the maximum allowable design ratio during this optimization process. It's 1.0, so you can set it to 90% or 80%, how you want to design your structure. Just as a hint. So let's summarize what we have done. We have exported the model from Tekla to RFEM, and we were able to continue working on it directly in RFEM, and we added this bracing. At the model, we defined some load cases and load combinations. We designed the cross sections, steel sections, and changed some or did some adjustments in our structure. Now we want to transfer all the changes we made to Tekla. So I go back to Tekla, close the analytical model, look from this side, and here we see again the Dlubal tab. We can import the model from RFEM. So if I click import from RFEM, the connection starts and RFEM will get locked. Okay, here's it. And now we have the opportunity to update this existing model. So we update the materials, cross sections, add new objects or remove objects. So we can say, okay, I want to update my existing model. And after some seconds, we will see the data transferred. It's locked. It's always take longer for the presentation for some reason. Okay. So you can see the bracing is now added in the structure. We have also a profile we defined in RFEM and also the material we defined in RFEM. We also see that these sections here are updated to the IPE 240. And we also see that already defined components remain in the Tekla model, even if we updated this cross-section in RFEM. So that's the workflow starting from Tekla model and design the structure in RFEM and transfer the changes back to Tekla, the changes we made in RFEM. Yeah, and what's missing for us now, only thing is missing that maybe I will show you shortly that we, of course, don't have the documentation for our steel design. So it's very simple for somebody who don't use RFEM. Maybe just to show it quickly, we have a printout report we can generate. We can save and show it, and the big value of RFEM 6 is that we can use this print report parallel to RFEM. So it's open us a new tab. You will see here in just a second. Here, so see the printout report and RFEM. So you can still work in RFEM and always look at your print report and update it like you want to have it. And all informations about the materials, about the sections, about the results are summarized in tables inside this report. And we can also illustrate information more clearly if we add some pictures to this report. So we can always add the current view of our model. So if I say like, okay, I have these sections in the table, I want to have it in a picture, I select the section in my model to be shown, and then I can say, okay, print this graph into my report. And after a short time, you will see you have some additional general settings for this picture. I will just save it. And now you see that this is directly added into our report. We can also define the steel design. Let me check. Let me activate the results. the steel design checks, and also just print it in our printout report if you want to visualize them in a picture. Save and show. And this is also directly put into our results folder down here. And when we say, okay, I don't like this view, I want to modify it, you can just edit the view and say, okay, I want to have it in a wireframe model. You can say, okay, and this picture will automatically be updated. And if you say, okay, that's fine, but I need more details about the design check, maybe about this critical design check, you can double click this design check and get shown all the formulas for this design check and also the notes from the used standard. And this also can be just printed in our report. And in this way you can store every information in your report you want to give to somebody else. Okay, so that's just a brief insight into the result documentation. And that's all from my side for this webinar. And I want to thank you for your attention. And I will hand back to Andreas.
Okay, Paul, thank you for this complete presentation, also with the printout report. Thank you for this. I would like to show the attendees where they can find the recording and the files and so on. Just let me hand over the screen to my screen. Okay. Yeah, just some additional information. If you want to book your free online appointment, such as a product demonstration, just contact our sales team with that link here, or you can scan the QR code. You can also download the PowerPoint slides from our website. I would like to show you where you can find that under dlubal.com. That's our quite new design of the website. And under news and events, you can find the webinars. Those are the webinars of the next weeks. And the next week, I will present that webinar together with Jürgen Teilmann, our regularly webinar about the most frequently asked questions. Then steel member design in RFEM 6. Then a webinar about the building model presented by Bastian Kuhn. Then, the other webinars of the next week, quite good overview. Then let me search for today's webinar. It's already accomplished. So I click on it. In the next days, you will get an email when the recording is online. You will get an attendee certificate with that email and with a direct link to that page. Then you will find the recording in the middle. And the PowerPoint slides are already here. And also the Tekla model and also the RFEM model. You can download all and repeat the webinar by yourself with the recording as you wish. Okay, that should be also all from my side. Thank you for your attention. Thanks to Paul for the nice presentation. Thanks to Lucas for answering the questions. I wish all a nice rest of the day and bye-bye.